Hi everyone, this is Dan from Earth Science Simplified and welcome to Inside of the Earth Part 2. So in Part 1 we talked a little bit about the layers, the depth to those layers, their composition, and we also touched on convection currents in the mantle. So if you haven't seen that, I highly recommend you go back, take a look, and it covers all of the basics. But for this video, let's start by looking at how we actually know what's inside of the Earth. I mean, we can't see it, the world's deepest mine is only about 4 kilometers below the surface. So what actually gives us the evidence? Well, we have several direct and indirect methods of seeing what's inside the Earth. Direct methods include looking at outcrops and the crust beneath our feet, and due to a mixture of tectonics and erosion, older deep crustal rocks are often brought up to the surface and exposed. We know that some of these rocks couldn't be formed at the surface as it's not hot enough, but they can be formed at certain depths thanks to the geothermal gradient. This gives us a rough idea on the structures and the rocks present at that particular depth. Another similar direct method is looking at the materials that volcanoes bring from depth. Firstly, the magma, which originates from the mantle, can tell us about mantle composition and chemistry, but also if you consider the power of some of these eruptions, you often get fragmented bits of upper mantle and lower crust which have been incorporated into the magma as it forces its way upwards through the rock. These rock samples include kimberlite, which can contain diamonds which form at very high temperatures and pressures. The last direct method we're going to look at is studying ophiolites. As I mentioned in previous videos, an ophiolite sequence is a section of oceanic crust that's been scraped off a descending oceanic plate at a subduction zone and thrust up onto the edge of the overlying continental plate. This pretty much eliminates the need for using boreholes as it gives us a complete oceanic sequence right down to the peridotite of the upper mantle. A really good real-life example of where ophiolites can be seen is in the Troodos Massif of Cyprus, which is where my next field trip is going to be, so hopefully I can bring you some really cool videos about that area. Now, moving on to the indirect evidence, so the stuff that we can't actually see, but that's inferred through other things. Firstly, the main one, seismic or earthquake waves. So earthquakes are caused through movement along the Earth's tectonic plates. Often these plates will move in varying directions and will get caught or stuck against one another, causing an ever-increasing amount of built-up energy. Eventually the strain gets too much and the two plates suddenly dislocate from one another, causing a sudden release of energy in the forms of seismic waves, or which you would feel as an earthquake. These seismic waves can travel through the entire Earth, and they can be detected by machines called seismographs. Seismic waves are broken up into P waves. These are the primary waves. They arrive first and they move in a pushing forward motion. S waves are the secondary waves. They're slower and arrive after the P waves, and they move in a shearing side-to-side motion, a bit like how a snake moves forward. Surface waves we'll cover later in a few lectures' time when we go into seismic waves a bit more. And finally, these waves move faster if the rock is more incompressible and rigid. Now, by incompressible, I mean less easily squished or compressed. So imagine if I was trying to squish a rubber ball in my hands and a foam ball in my hands. Now the rubber ball is going to want to spring back into shape much more quickly because it's more incompressible, it offers more resistance. Now when this happens, when I remove the pressure, it's going to fire my hands away at a faster rate as it springs back into shape. And this applies to P waves. So as they compress the rock, the more incompressible material will want to get back into shape more quickly and move the wave along faster. Now by rigidity, in this case I mean how much it's going to resist being bent out of shape. If you're an S wave moving side to side and you have a material that's easily moved about, you're just going to keep moving to one side without it forcing you to go back in the other direction, so you'll never really move forward. So a more incompressible rock means faster P waves, and a more rigid rock means faster S waves. Now I know this is a bit confusing, so don't worry too much about it now if you don't really understand. As I said before, it will be covered in much more depth in a few lectures' time. Now finally, a wave moves much more slowly through denser rock, as there's simply just more things that it has to move through. It's like in real life. If you walk through an empty street, you're going to move through it much faster than a busy one. So how does this tie into knowing what's inside of the Earth? Firstly, it can tell us if a layer is liquid or solid. As a liquid offers no rigidity, S waves can't move through it. They just move off to one side and they lose their energy. So if you look at the diagram here, you can see an earthquake that occurs at 0 degrees, so the North Pole in this case, will fire off all of these S waves. And because the outer core is liquid, none of these S waves can travel through it. This creates a shadow zone here, which is an area where no S waves will be detected by seismometers. This zone is generally between 103 degrees, either side of where the earthquake originates. Now P waves also have their own shadow zone, and this is due to refraction. Refraction is where a wave is deflected, so its path is changed. And this happens when a wave goes into an area of different properties, meaning it can travel at a different speed. So naturally, when a wave hits a new layer of the Earth, its course is going to be slightly changed due to the new properties. In this diagram, you can see that any wave that hits the outer core, so originating here, moving inwards, hitting the outer core, is going to be refracted slightly inwards, and again when it reaches the other side of the mantle. Any wave that doesn't hit the core just continues on its normal path. This again creates a shadow zone for the P waves that exists between 103 to 142 degrees on either side of where the source is. Again, we can use this to infer the boundary and the change in state between the mantle and the outer core. And finally, one of the more simple ways of using seismic waves to detect boundaries is through reflection. So rather than the pathway of the wave being refracted, when a wave hits a layer of new properties, some of the energy can simply bounce back towards the Earth's surface, as shown in the diagram. Geophysicists can often use this to map the subsurface in exploratory geology to produce profiles like this. So for our last indirect method, we're going to look at meteorites. The Earth shares a common origin with most other planets and debris within the solar system. It's all formed from the same stuff. The only difference is our Earth has undergone many different processes since then, like differentiation. And our crust to rock is subject to metamorphism and lots of different kinds of alteration. It can, however, give us some insight into the rough composition of the mantle and the core. So just at the end, for revision purposes, I'll put up these summary sheets which you can just screenshot or copy for your notes. So here's the direct evidence for the structure of the Earth, and here is the indirect evidence for the structure of the Earth. I hope you enjoyed the video, and stay tuned for our next one, where we take a quick look at the geological timescale.